Now, continuing our discussion of electrical measurements, let's take a look at frequency measurement. Most frequency counters work by measuring the number of times the waveform crosses the zero line in a specific time. Power system frequency, say 50 or 60 hertz, is fairly straightforward to measure. However, high-frequency communication channels are more difficult. We often need to measure signal strength at a specific frequency. If multiple frequencies are present in the signal, the frequency meter will not measure accurately. In this case, a spectrum analyzer may be used to examine the signal across a wide frequency range so as to detect the presence of unsuspected additional signals. When the signal frequencies are known, then a selective voltmeter can be used to check the signal strength at any selected frequency. In practice, the instrument is set up to respond to a band of frequencies either side of the selected frequency. The selective voltmeter actually filters out all other frequencies. The range of frequencies measured is known as the bandwidth. In this example, we have two signals, one at 9 kilohertz and the other at 10 kilohertz. This is the reading of the 9 kilohertz signal when a narrow bandwidth is selected. When we increase the bandwidth, the measured signal strength increases considerably due to influence from the second frequency. The bandwidth must be chosen so as to prevent energy from adjacent signals causing a measuring error. With the narrow bandwidth selected, we measure the signal strength in dBs of just the 9 kilohertz signal. On the wide bandwidth setting, we get a higher dB reading. Now hang on. What is this dB value? Well, you may remember that we talked about dB, that is decibel signals, in an earlier tape on communication systems. It is common practice to use the dB notation when measuring signal strength on communication circuits. The reason for this is that at the low values of signal strength often encountered in communication circuits, the dB scale is much more accurate to use. For example, look at these three voltages displayed on a linear voltage graph. You can see that it is quite difficult to accurately plot or read the very low voltage of 0.07746. Now compare this with the same voltage levels on a dB scale. Obviously, plotting the dB levels provides much greater accuracy. This is because it is in fact a logarithmic scale. The dB value is a logarithmic representation of the voltage magnitude. Let's briefly review the principle of dB measurement, which has a corresponding power level at a specified resistance value. Note that the dB scale consists of plus and minus levels. Conventionally, the 0 dB point is defined as the specific voltage which will dissipate 1 milliwatt when connected to a 600 ohm resistor. If you calculate this out, it comes to 0.7746 volts. This is RMS value, of course. The value of 600 ohms was chosen because this is approximately equal to the characteristic impedance of most telephone lines. To be precise, the value of 0.7746 volts would be written as 0 dBm bracket 600. The little m indicating 1 milliwatt and the 600 confirming that the scale is referenced to 600 ohms. But what about other values of voltage? Well, this is related to the 0 dB equivalent voltage by the following expression. dBm bracket 600 equals 20 times log V2 divided by 0.7746. Where V2 is, say, 0.427 volts, this particular calculation comes to a value of minus 5.17 dBm bracket 600. This minus value does not mean that the voltage is negative, only that it is lower than the reference voltage. Whenever you're using dB scales or dB measuring instruments, always check the reference values, usually 600 ohm and 1 milliwatt. This is important because you may have to apply correction factors based on this information. An example of this is shown in your workbook. Many dB meters are provided with a selector switch marked bridged or terminated. The bridged selection should be used when you wish to perform dB measurements on a circuit which is already properly terminated. In the bridged position, the impedance of the meter is high, therefore having negligible effect on the circuit. However, in some cases, you may wish to measure the signal strength directly from a transmitter or signal generator with the outgoing circuit disconnected. For this purpose, the selector should be switched to the terminated position. This will now switch a 600 ohm resistor across the output to simulate the circuit impedance. Other values of resistance can be selected, say 50 or 75 ohm, depending upon the reference values required. All right, so far in this segment, we have been looking at frequency measurement and measurement of signal strength in dB. Now let's move along to look at another very important measuring instrument, that is the timer. Timing measurements can be performed by an oscilloscope, chart recorder, or digital timer. The digital timer is the most accurate but may still give false readings if certain precautions are not taken. For example, here we have a Doble FT2 timer which is set up to measure the dropout time of a relay. The timer will start when the relay coil is de-energized and will stop when the relay contacts open. But look, this relay operates on 125 volts DC. As we have mentioned before, when the DC current is interrupted, the magnetic field set up by the current collapses. This in turn may induce a voltage in the stop circuit, which can cause current to flow in a direction such that a premature stop signal will be produced. In fact, the timer will probably read 0. One possible solution to this problem might be to connect a diode across the coil, which slows down current decay. However, this may prolong the current flow through the coil enough to have a significant effect on the dropout time of the relay. Another possible solution is to keep the stop circuit leads as short as possible and twist them together. A better solution yet would be to install a special solid-state switch, such as the one shown here, which is not affected by magnetic induction. A description of this is included in your workbook to give you more time to study the circuit. All right, now let's turn our attention to measurement of phase angle. Correct phasing is essential for generator operation, relay directionality, and metering. Most phase angle meters work on the same principle, that is, to measure the time interval between the zero crossing of the two quantities. There are 360 degrees in one complete cycle, so the circuit is designed to convert the measured time difference into a phase angle reading. When using the instrument, great care must be taken to make sure that the circuits 1 and 2 are clearly identified, also that the polarity marks are followed. Let's look at a simple example. Here we are trying to check the phase angle difference between current and voltage, and also to check that phase rotation is correct. Our reference voltage is connected to circuit 1. As this is from the A phase, it is indicated on our phasor diagram as VA. Now, using the correct test plugs, current IA is connected to the circuit number 2 on the instrument. The phase angle is measured and shown as plus 333 degrees. So the current IA can be plotted like this on our phasor diagram. You can see that the phase angle between current and voltage is actually 27 degrees lag. Now repeat the procedure for the other two phases, current IB and IC. The results are plotted as shown here. We can see that all three phases are balanced and that phase rotation is correct. That is, IA, IB, IC in the counterclockwise direction. In order to calculate the phase angle, The instrument must very precisely measure frequency of the signals and time. Suppose in this test that the frequency was precisely 60 hertz. What would be the measured time interval between VA and IA? The time for one cycle, that is 360 degrees, will be 1 second divided by 60 equals 16.66 milliseconds. The time interval for a phase difference of 27 degrees is therefore equal to 16.66 times 27 divided by 360 equals 1.25 milliseconds. So you can see how accurate the timing measurement must be. Up to this point, we've taken a broad look at electrical measurements that are typically required in testing and calibrating protection schemes. One particularly useful measuring instrument that we have not yet discussed is the oscilloscope. We'll be looking at this in the next segment. For now, it's time for a break, so please switch off the tape and thoroughly review this material in your workbook.